Right now, at this very moment, two massive objects are moving through our solar system. One travelled from another star, crossing the unimaginable void between solar systems to arrive at our doorstep. The other has been lurking in the darkness, at the edge of our cosmic neighbourhood for millions of years, and it's now making its slow, deliberate approach inward. Both are real. Both are here. And one of them should absolutely capture your attention in ways you haven't considered. But here's the question that's been burning in my mind, the question that kept me digging through research papers and observation reports late into the night. Which one actually matters? Which one should we be talking about? Which one deserves not just our curiosity but our genuine concern? You've probably heard about the interstellar visitor. The comet from beyond, the stranger that doesn't belong here, the cosmic anomaly that's been making headlines and capturing imaginations. And yes, it's extraordinary. A visitor from another star system is always going to turn heads. It's the celebrity of the solar system right now, the object everyone wants to photograph, the trajectory everyone wants to calculate. But while we've been watching that interstellar stranger, something else has been moving through the outer darkness. Something so massive, so unprecedented in scale, that when scientists first detected it, they thought it might be a dwarf planet. Something that's been forgotten in the buzz around the interstellar visitor. Something that might actually be far more significant than the object stealing all the attention. I'm talking about UN271, Comet Bernardinelli-Bernstein, if you want its full name. And if you haven't heard of it, that's exactly the problem. Because while one object gets the spotlight for being exotic, the other represents something potentially more important. A window into threats we barely understand. A reminder of what's actually out there in the frozen reaches of space waiting. So let me ask you directly. Which one should terrify you? The interstellar stranger that came from somewhere else and will leave forever, never to return? Or the giant from our own backyard? An object so large it defies what we thought we knew about comets. Something that will come back. Something that represents not just itself, but an entire population of objects we're only beginning to comprehend. One comes from impossibly far away. One has been here all along, hiding in the dark. Both are moving. Both are massive. But only one changes how we should think about cosmic threats. And here's what makes this comparison so crucial. The answer isn't what you think. It's not obvious. It's not simple. Because when you actually look at the data, when you compare trajectories and sizes and origins and what these objects tell us about the universe, the conclusion is surprising, maybe even uncomfortable, because it forces us to confront something about how we perceive danger, how we assess threats, how we decide what deserves our fear and what deserves our wonder. Stay with me for the next several minutes because we're going to do something most coverage hasn't done. We're going to put these two cosmic giants side by side. We're going to look at their sizes, their origins, their trajectories, what they mean for Earth, and what they reveal about the universe we live in. We're going to compare the interstellar celebrity with the forgotten monster, and by the end, I promise you, your perspective on which one matters more will shift. You'll understand why one of these objects represents not just a scientific curiosity, but a genuine wake-up call about vulnerabilities we haven't fully grasped. So here's what I need from you. Hit that like button if you're ready to face what's actually out there. If you're willing to look beyond the headlines and understand what these objects really mean. Drop a comment right now telling me which one you think is more dangerous, the visitor from another star or the giant from our own solar system's frozen edge. Because I'm genuinely curious where you stand before we dive deep into this comparison. By the time we're done, your answer might change completely. You might realize that the object getting all the attention isn't the one we should be focused on. Or you might discover that both objects matter, but for completely different reasons than you imagined. Either way, what we're about to explore will change how you think about cosmic threats. Let's find out which giant really deserves to keep you awake at night. Let's start with the object everyone's talking about, the interstellar visitor, the comet that came from somewhere else. Right now, in November of this year, 3I Atlas is making its way through our solar system, and the scientific community is watching its every move. This isn't just another comet. This is something that formed around a completely different star in a planetary system we'll never see, under conditions we can only guess at. It was violently ejected from its home, sent tumbling through the galaxy, travelling through interstellar space for who knows how long, until it happened to encounter our sun's gravitational influence and fell inward toward us. Think about that journey for a moment. This object wasn't born here. It doesn't belong to our family of planets and moons and asteroids. It's a traveller, a wanderer, something that experienced the cold darkness between stars and somehow survived to tell the tale. And that alone makes it extraordinary. This is only the third confirmed interstellar object we've ever detected passing through our solar system. The first was Oumuamua, that strange elongated object that sparked countless theories. The second was 2I Borisov, another interstellar comet that gave us our first real glimpse of what comets from other stellar systems might look like. And now we have 3I Atlas, our latest visitor, our most recent window into the cosmic neighbourhood beyond our Sun. What makes this comet particularly fascinating is that it's behaving like a comet should. It's not mysterious and cigar-shaped like Oumuamua. It's not confusing scientists with unexplained accelerations that fuel wild speculation. It's actually doing exactly what a comet does. It's outgassing, producing tails, glowing with reflected sunlight and its own activity. And that's actually more valuable scientifically than something bizarre and inexplicable. Because when something behaves as expected, we can learn from it. We can study its composition, understand what another stellar system produces, compare it to our own comets, and see what's similar and what's different. The nucleus of 3I Atlas, the solid core beneath all that gas and dust, is estimated to be several kilometres across. Not enormous by comet standards, but certainly substantial. And what's remarkable is how active it is. Despite travelling through the freezing void of interstellar space, despite being exposed to cosmic radiation and the absolute cold of the galaxy, this comet still has volatiles, ices that can sublimate, that can turn from solid to gas and produce the spectacular displays we associate with comets. It's been observed developing multiple tails, complex structures in its coma, all the hallmarks of an active, dynamic object responding to the sun's heat as it makes its closest approach. NASA has been tracking it. The European Space Agency has been tracking it. Observatories around the world have been pointing their instruments at this visitor, capturing images, analysing spectra, measuring the composition of its outgassing. They're looking for organic molecules, for water ice, for carbon dioxide and carbon monoxide, and all the chemical signatures that tell us about the building blocks of planetary systems. Because every measurement we take of 3I Atlas tells us something about the star system it came from. Every data point is a glimpse into a place we can never visit, a planetary system that might be hundreds or thousands of light years away. There's been some speculation recently about unusual characteristics, claims about unexpected mass distributions, strange rotation patterns, things that might make this comet even more unique than we first thought. But here's where we need to be careful, where we need to separate confirmed science from preliminary findings. These claims are based on early research, observations that are still being analysed and debated. They haven't been confirmed through the rigorous peer review process that separates speculation from established fact. And that's important to acknowledge, because in the rush to make discoveries seem more sensational, we can sometimes get ahead of what the data actually supports. What we do know for certain is that 3I Atlas is following a hyperbolic trajectory. That's the mathematical signature of an interstellar object, a path that isn't bound to the sun, a curve that means this comet will slingshot around our star and then leave forever, accelerating back out into the galaxy. It's a one-time visitor. We get this brief window to observe it, to learn from it, to study what another star system produces, and then it's gone. In a few years, it'll be too faint to observe. In a few decades, it'll be back in interstellar space, heading towards some unknown destination in the galaxy. And this is where it gets interesting, because as extraordinary as 3I Atlas is, as much attention as it's receiving, it's also exactly what it appears to be: a visitor, a passerby, something that will never threaten Earth, never come close to our orbit, never return to give us a second chance at observation. It's spectacular, yes. It's scientifically valuable, absolutely. It's giving us insights into how planetary systems form, how objects get ejected into interstellar space, what survives the journey between stars, but it's also temporary, fleeting, here and then gone. The missions that are currently exploring the outer solar system, Europa Clipper heading to Jupiter's moons, JUICE on its way to study the Jovian system, they're catching glimpses of this visitor as it passes through their field of view. These spacecraft weren't designed to study interstellar objects, but they're adding their observations to the growing dataset, contributing to our understanding of what 3I Atlas is and where it might have come from. Every telescope, every spacecraft, every amateur astronomer with the right equipment, They're all part of this global effort to squeeze as much knowledge as possible from this brief cosmic encounter. So that's 3I Atlas, that's the interstellar stranger, an object from another star, travelling through our solar system on a trajectory that will take it away forever, active, spectacular, scientifically valuable, and completely safe. It's not going to hit Earth. It's not going to disrupt planetary orbits. It's not a threat in any conventional sense. It's a gift, a chance to study something exotic, something that formed under different conditions, something that gives us a glimpse beyond our own stellar neighbourhood. And that's worth celebrating, worth studying, worth the attention it's receiving. But now let me introduce you to the other object in our comparison, the one that hasn't been getting the headlines, the one that's been quietly approaching from the frozen darkness at the edge of our solar system, the one that might actually matter more in ways we haven't fully appreciated, because while 3I Atlas is extraordinary for where it came from, there's another giant moving through space that's extraordinary for what it is, for its sheer, almost incomprehensible size, and for what that size tells us about the hidden population of objects lurking in the outer reaches of our solar system. Now let me tell you about something that should have been front-page news, something that should have captured the world's imagination, but somehow slipped through the cracks of public awareness. While everyone was focused on interstellar visitors and the exotic mysteries of objects from other stars, a team of astronomers discovered something in our own solar system that changed what we thought we knew about comets. They found a giant, not just a large comet, but something so massive, so unprecedented in scale, that it defied categories. Something that had been hiding in plain sight, moving through the outer darkness for years before anyone realized what they were looking at. The story begins in Chile, at the Cerro Tololo Inter-American Observatory, where an enormous survey called the Dark Energy Survey was scanning the southern sky night after night, mapping galaxies, measuring cosmic expansion, trying to understand the fundamental nature of the universe. But while searching for the largest structures in existence, the survey kept capturing something much closer to home, something moving slowly against the background of stars, something that kept appearing in image after image year after year. Nobody paid much attention at first. The Dark Energy Survey was designed to look at distant galaxies, not nearby solar system objects, but the data was there, accumulating, waiting for someone to notice. That someone was Pedro Bernardinelli and Gary Bernstein, researchers who were sifting through the survey's archives, looking for anything unusual, anything that moved, anything that might be worth a closer look. And in the data from observations dating back years earlier, they found it. An object moving in the outer solar system, far beyond Neptune, travelling on an orbit that would eventually bring it closer to the Sun. At first, they weren't sure what they had found. The object was so large, so massive, that it looked more like a dwarf planet than a comet. It wasn't behaving quite like anything they'd seen before. But as they gathered more observations, as other astronomers joined the hunt and pointed telescopes at this mysterious object, the truth began to emerge. This wasn't a dwarf planet. This was a comet, the largest comet ever observed. The largest comet, in fact, by such a massive margin that it redefined what we thought comets could be. And it had been there all along, moving through the frozen reaches of the Oort Cloud, that vast shell of icy bodies that surrounds our solar system, at unimaginable distances, where comets are born and where they wait, sometimes for millions of years, before something disturbs their orbits and sends them falling inward toward the Sun. They named it C-2014 UN271, using the designation from the year its earliest images were captured. But it's also known as Comet Bernardinelli-Bernstein, after the two astronomers who pulled it from the archives and recognized its significance. And when they calculated its size, when they measured its brightness and used that to estimate how big the nucleus actually was, they realized they were looking at something extraordinary, something that shouldn't exist according to what we thought we knew about comet populations. Then the Hubble Space Telescope got involved. Hubble, the most famous observatory in history, the telescope that's given us the deepest views of the universe, turned its gaze toward UN271, and Hubble confirmed what the initial observation suggested. The nucleus of this comet, the solid ice and rock core beneath all the gas and dust, is approximately 80 to 85 miles across. Let that sink in for a moment. 85 miles. That's not a typo. That's not an exaggeration. That's the actual confirmed size of this object's nucleus. That's larger than Rhode Island. That's bigger than many cities. That's a mountain of ice and rock drifting through space, so massive that if you stood on one side of it, the other side would be beyond the horizon. To put this in perspective, most comets, the ones that occasionally swing by Earth and put on spectacular shows, the ones that get named after their discoverers and appear in the night sky with beautiful tails, have nuclei that are just a few miles across, maybe 10 miles at most. Even famous comets like Halley's Comet, which has been observed for thousands of years and returns every 76 years, has a nucleus that's only about 10 miles long. UN271 is 10 times bigger than that. It's 50 times larger than typical comet nuclei. It's in a category entirely by itself. So far beyond normal comet sizes that it almost seems like a different type of object altogether. And the mass, the sheer amount of material packed into this frozen giant, is estimated at around 500 trillion tons. That's a number so large it becomes almost meaningless. 500 trillion tons of ice and rock and organic compounds and whatever else makes up the ancient, pristine material from the early solar system. This object has more mass than any comet ever observed. It's not just bigger, it's fundamentally different in scale, in significance, in what it represents about the population of objects lurking in the Oort Cloud. Because here's what makes UN271 so important. If one comet this massive exists, if the Oort Cloud can produce something this enormous, then what else is out there? How many more objects of this size are drifting in the darkness too far away to see, too distant to detect, waiting for some gravitational nudge to send them inward? We've always known the Oort Cloud contains billions of comets, maybe trillions, but we thought they were all relatively small, the kind of objects that occasionally drop into the inner solar system and give us a nice light show. UN271 suggests we were wrong. It suggests there might be giants lurking out there, massive objects that could, under the right circumstances, make their way toward the inner solar system where Earth lives. And what makes this even more remarkable is that UN271 is already active. Even though it's still incredibly far from the Sun, even though it's experiencing only a fraction of the solar heating that normally makes comets come alive, it's already outgassing. Observations from ALMA, the Atacama Large Millimeter Array, one of the most powerful radio telescope networks on Earth, have detected carbon monoxide jets streaming from UN271's surface. The comet is shedding material, producing a faint coma, behaving like an active comet despite being at distances where most comets remain frozen and dormant. This tells us something profound about UN271's composition. It's not just a dirty snowball, it's rich in volatiles, in materials that can sublimate even at incredibly low temperatures. The carbon monoxide jets suggest a complex chemical composition, a mixture of ices and organic molecules that have been preserved since the solar system's formation. This object is a time capsule, a frozen record of what the outer solar system was like when the planets were still forming, when everything was chaos and collisions and icy bodies were being scattered in all directions by the gravitational influence of Jupiter and Saturn and the other giant planets. UN271 originated in the Oort Cloud, that spherical shell of comets that extends halfway to the nearest star. It's been out there for millions of years, orbiting the Sun so slowly, so distantly, that it's barely been touched by solar radiation, barely been altered by time. And now it's making one of its rare journeys inward, falling toward the Sun on an orbit that will take years to complete, moving from the frozen outer darkness toward the warmth and light of the inner solar system. Not close enough to threaten Earth, not close enough to become a spectacular naked-eye comet, but close enough for our telescopes to study, close enough for us to learn from, close enough to teach us about the vast population of objects we've barely begun to understand. So that's UN271. That's the monster you've never heard of. A comet so large it was mistaken for a dwarf planet, so massive it redefined what we thought comets could be, so ancient and pristine that it's giving us insights into the solar system's birth. It's not exotic like the Interstellar visitor, it's not from somewhere else. It's been here all along, part of our solar system's family, part of the vast cloud of frozen bodies that represents the leftover material from planetary formation. But in its own way, UN271 is just as extraordinary as any interstellar object, maybe more so, because it shows us what's possible in our own cosmic backyard, and that might be more important than anything arriving from the stars beyond. So now we have both objects on the table, the interstellar stranger travelling from another star system, and the giant from our own frozen frontier. And here's where we need to put them side by side, where we need to compare them directly, because only through comparison can we understand which one truly deserves our attention. Let's talk about size, because size matters in astronomy. It matters for gravitational influence, for scientific value, for understanding what these objects can tell us, and yes, for assessing any potential threat they might pose. 3I Atlas has a nucleus estimated at several kilometers across. That's substantial for a comet. That's enough mass to produce spectacular tails, enough volatiles to create beautiful displays as it responds to solar heating. If this comet were to somehow, impossibly, hypothetically, hit Earth, it would be catastrophic. But it's not going to, and that's important to remember. What matters here is understanding the scale of what we're dealing with. Several kilometers of ice and rock, travelling through our solar system, active and dynamic and scientifically valuable. UN271 has a nucleus of approximately 80 to 85 miles across. Let me say that differently. The nucleus alone, not the coma, not the tail, just the solid core of ice and rock, is wider than the distance between major cities. It's larger than some of the smaller states. It's so large that if you could stand on its surface and look in any direction, you'd see a horizon. You'd see the curve of this frozen world extending away from you. This isn't just a comet. This is something that approaches the scale of a small planet. Something so massive it exists in a completely different category. The mass comparison is even more striking. 3I Atlas is estimated to contain tens of billions of tons of material. That's an enormous amount of ice and rock. That's enough mass to make a serious impact if it were on a collision course with anything. But UN271 contains 500 trillion tons, not billions, trillions. The difference between these two objects is like comparing a boulder to a mountain range. Both are impressive in their own right, but they're not even in the same category of magnitude. And this size difference matters for more than just dramatic comparisons. It matters because it tells us about how these objects formed, what conditions created them, what their parent systems were capable of producing. 3I Atlas formed around another star, in a planetary system we'll never see. Its size suggests it formed in the typical region where comets are born, in the outer reaches of a stellar system, where temperatures are low enough for ices to condense, where rocky material mixed with frozen volatiles to create the building blocks of comets. It's representative of what we'd expect from comet formation in most planetary systems. UN271, on the other hand, is an anomaly. Its size suggests something unusual about either the conditions in which it formed or the mechanisms that scattered it into the Oort Cloud. To grow this large, it needed access to enormous amounts of material. It needed to form in a region of the early solar system where ice and rock were abundant, where collisions could build up mass gradually, where it could accrete material without being disrupted by gravitational interactions. And then something, probably Jupiter's gravity, or Saturn's, or some combination of planetary perturbations, flung it outward, sent it on a trajectory that carried it to the Oort Cloud, where it's been preserved ever since. The activity patterns are interesting too. Both comets are active, both are producing coma and tails, both are responding to solar heating by releasing gases, but the nature of their activity is different. 3I Atlas is active because it's approaching the Sun after travelling through interstellar space. Its volatiles, the ices that sublimate when heated, are relatively near the surface, exposed by the erosion and weathering of its long journey. When sunlight hits these volatiles, they turn to gas, producing the spectacular displays we observe. UN271 is active despite being incredibly far from the Sun, far beyond the orbit of Neptune, in a region where temperatures are so low that most materials remain frozen solid. The fact that it's producing carbon monoxide jets at these distances tells us something important about its composition. Carbon monoxide is more volatile than water ice. It can sublimate at lower temperatures, can respond to even the faint heating from a distant sun. This suggests UN271 has a complex internal structure, with different layers of varying composition, different ices that respond to different temperature thresholds. The coma structures are also telling. 3I Atlas has developed multiple tails, complex patterns in its coma that suggest non-gravitational forces are at play. These are forces caused by outgassing, by jets of material erupting from specific locations on the comet's surface, causing the nucleus to rotate or wobble or accelerate in ways that pure gravity can't explain. This is normal for active comets. This is what we expect to see. And for 3I Atlas, it's giving us valuable data about how interstellar objects behave when they encounter a new star's heat, after travelling through the cold of interstellar space. UN271's Comet is less spectacular, but perhaps more scientifically important. Because it's so far from the Sun, because the heating is so minimal, every bit of activity we observe is significant. The carbon monoxide jets aren't random. They're coming from specific locations, suggesting active regions on the nucleus, places where subsurface ice is exposed and can respond to solar heating. These jets are telling us about the internal structure of this giant comet, about how heat penetrates into its interior, about what materials lie beneath the surface. Size also determines observational opportunities. 3i Atlas, being smaller and more typical in scale, is bright enough to observe only when it's relatively close to the Sun, when solar heating is driving enough activity to make the comet visible. As it moves farther away on its hyperbolic trajectory, it will fade, becoming harder and harder to detect, until eventually it's too dim for even our most powerful telescopes to follow. We have a limited window to study it before it's gone forever. UN271, because of its enormous size, remains observable even at extreme distances. Its nucleus is so large that it reflects enough sunlight to be detected even when it's far beyond Neptune, even when it's in regions where smaller comets would be completely invisible. This gives us years of observation time, years to study its approach, to watch how its activity changes as it gets closer to the Sun, to understand how giant comets behave over long timescales. This is an opportunity we've never had before, to watch a comet of this size over an entire orbital approach, from the distant Oort Cloud inward toward the inner solar system. So when we compare sizes, when we look at the mass and scale and activity patterns of these two objects, UN271 dominates. It's larger by an order of magnitude. It's more massive by factors that make comparison almost meaningless. It's representative of a population of objects we barely understand, a category of comet that might be far more common in the Oort Cloud than we ever suspected. 3i Atlas is spectacular for where it came from, but UN271 is spectacular for what it is, a genuine giant, a reminder that our solar system still holds surprises, still contains objects we're only beginning to discover and understand. And that brings us to the next crucial question in our comparison. Where did these giants come from? Because origin stories matter. They tell us about how planetary systems form, how objects get scattered and ejected, how the universe creates the diversity of worlds and comets and asteroids we observe. Let's trace both objects back to their beginnings and understand what their origins reveal about the cosmos we inhabit. Every object in space has a story, a history written in its composition and orbit, and the trajectory that brought it to where we observe it today. And when we look at 3i Atlas and UN271, when we trace their paths backward through time, we find two radically different origin stories, one from the chaos of another stellar system, one from the frozen archives of our own solar system's birth. Understanding where these objects came from helps us understand what they mean, what they represent, and why their existence matters for our broader understanding of the universe. 3i Atlas was born around another star. We don't know which star. We can trace its trajectory backward, try to calculate where it came from, try to identify candidate stars that might be its home system. But interstellar space is vast and orbits are chaotic, and the truth is we may never know exactly where this comet originated. What we do know is that it formed in the outer regions of some planetary system, probably similar to our own, where temperatures were cold enough for water ice and carbon dioxide and other volatiles to condense out of the protoplanetary disk and begin sticking together. Imagine that system billions of years ago. A young star surrounded by a disk of gas and dust, with planets beginning to coalesce from the material swirling around it. In the inner regions, close to the star where temperatures are high, rocky planets form, worlds like Earth and Mars and Venus. But farther out, beyond some distance that astronomers call the ice line, temperatures drop low enough for ices to form, and this is where comets are born, where the building blocks of frozen worlds begin to accumulate. 3i Atlas would have started as just dust and ice, tiny particles colliding and sticking together through static electricity and gentle gravitational attraction. Over time, these collisions built up larger bodies. Pebbles became boulders, became mountains of ice and rock. Eventually, somewhere in that distant planetary system, 3i Atlas grew to its current size of several kilometers, a typical comet nucleus, a frozen time capsule containing the chemical composition of its birth system. But then something happened. Something violent. something that took this comet from its home orbit and flung it into interstellar space. This is the part of the story we can only guess at because we weren't there to observe it, and we may never know the details. But we know the mechanisms that can eject comets from planetary systems. Most likely, 3I Atlas had a close encounter with a giant planet, something like Jupiter or Saturn, a massive world with gravity strong enough to deflect comets onto escape trajectories. Or perhaps its home system experienced a stellar encounter, another star passing close enough to gravitationally disturb the orbits of everything in the outer system, sending comets and asteroids scattering in all directions. Whatever the cause, 3I Atlas was ejected. It left its home system and began a journey through the galaxy. And this journey, this long drift through interstellar space, is what makes this comet so scientifically valuable. It travelled through the galaxy for an unknown amount of time. Could have been thousands of years, could have been millions. During that journey it was exposed to cosmic radiation, to the faint dust and gas of the interstellar medium, to conditions that no object in our solar system ever experiences. It was weathered by this journey, altered by it, shaped by the harsh environment between the stars, and then, purely by chance, its trajectory brought it near our Sun. The Sun's gravity began to pull on it, began to curve its path, and 3I Atlas fell inward, becoming the third confirmed interstellar object detected passing through our solar system. It's a visitor, a wanderer, something that gives us a glimpse into planetary formation around other stars. Every measurement we take of its composition tells us something about its home system, what elements were present, what conditions existed, what that distant protoplanetary disk was made of billions of years ago. UN271's origin is completely different but just as fascinating. This comet was born right here, in our own solar system, during the chaotic era when the planets were still forming and the entire system was a dynamic, violent place of collisions and migrations and orbital rearrangements. It formed in the outer reaches of the protoplanetary disk, beyond where Neptune orbits today, in a region where ices were abundant and collisions could build up large bodies relatively quickly. But unlike the planets, which managed to stay in relatively stable orbits and continue growing until they became the worlds we see today, UN271 was disturbed. Something, most likely the gravitational influence of the giant planets as they migrated and settled into their current orbits, grabbed UN271 and flung it outward, not out of the solar system entirely, not into interstellar space, but into the Oort Cloud, that vast spherical shell of comets that surrounds our solar system at enormous distances, extending halfway to the nearest star. The Oort Cloud is where comets go to wait. It's a reservoir of frozen bodies, leftovers from the solar system's formation, objects that were scattered outward by planetary gravitational interactions but remained weakly bound to the Sun. These comets orbit at such enormous distances that they barely feel the Sun's heat, barely experience any change from their primordial state. They've been there for billions of years, preserved in the deep freeze of space, waiting for something to disturb their orbits and send them falling back inward. For UN271, that disturbance came relatively recently in cosmic terms. Something perturbed its orbit, maybe a passing star, maybe the gravitational influence of the galaxy itself, maybe just the accumulated effects of tiny perturbations over millions of years. Whatever the cause, UN271's orbit changed. It began falling inward toward the Sun on a journey that will take it from the outer reaches of the Oort Cloud all the way to the inner solar system and then back out again. This is its grand tour, its return to the solar system's inner regions after millions of years in cold storage. And what makes UN271 so valuable scientifically is that it's giving us access to pristine solar system material. This comet hasn't been repeatedly heated by the Sun. It hasn't made dozens of passes through the inner solar system, losing volatiles each time, becoming a dead, inert husk. It's making what might be only its second or third approach since it was first scattered into the Oort Cloud billions of years ago. That means its composition is almost unchanged from the solar system's formation. It's a time capsule, a frozen sample of the protoplanetary disk that surrounded our young Sun when Earth was just beginning to form. The size of UN271 tells us something important about the early solar system. To grow this large, to accumulate this much material, it needed to form in a region where ices and rocks were abundant, where the density of material was high enough for rapid growth. This suggests that the outer solar system, during the era of planetary formation, was rich with material, capable of producing not just typical-sized comets, but genuine giants. And if UN271 exists, if the Oort Cloud contains at least one object of this scale, then there are probably others. We just haven't detected them yet because they're too far away, too faint, orbiting in the darkness beyond our current observational capabilities. So here's what these origin stories tell us. 3i Atlas shows us that other stellar systems produce comets, that planetary formation around other stars follows similar processes to what happened in our solar system, that the galaxy is full of wandering objects that were ejected from their home systems and now drift through interstellar space. UN271 shows us that our own solar system is more complex than we realized, that the Oort Cloud might contain giants we never suspected, that the population of long-period comets includes objects of extraordinary size that could, under the right circumstances, make their way into the inner solar system where Earth resides. One origin is exotic, interstellar, a window into distant planetary systems we'll never visit. The other origin is local, ancient, a reminder of what happened here billions of years ago and what might still be lurking in the frozen reaches of our own cosmic neighbourhood. Both stories are important. Both teach us something about how planetary systems form and evolve. But they're fundamentally different in what they imply about threats, about discovery, about what we should be watching for in the decades and centuries ahead. Which brings us to the central question, the one that's been building through this entire comparison. What about their trajectories? Where are these objects going? How close will they come to Earth? And is there any real danger, any legitimate reason to be concerned about either of these cosmic giants? Let's follow their paths and find out what their orbits tell us about threat and safety and the real meaning of cosmic danger. This is the moment we've been building toward, the question that matters most when we talk about comets and asteroids and anything moving through our solar system. What are these objects actually going to do? Where are they going? How close will they come? Should we be worried? Because you can have the most massive comet in history. You can have the most exotic interstellar visitor ever detected. But if their trajectories don't bring them anywhere near Earth, if their orbits keep them safely distant, then the threat level is very different from what the word Terrify might suggest. Let's start with 3i Atlas, because its trajectory is actually the simpler of the two to understand. This comet is following what astronomers call a hyperbolic orbit. That's a mathematical term that describes a path that isn't closed, that isn't an ellipse looping around the Sun again and again. A hyperbolic orbit is open-ended, a curve that comes in from infinity and goes back out to infinity. It's the trajectory of something just passing through, something that isn't gravitationally bound to the Sun, something making a one-time visit and then leaving forever. 3i Atlas came in from interstellar space, approached the Sun, and is now heading back out. Right now, in November of this year, it's in the process of making that outbound journey, moving away from the inner solar system, fading from view as it gets farther from the Sun, and stops being heated enough to produce the spectacular activity that makes comets visible. And here's the critical point. Its trajectory never brought it close to Earth, not even remotely close. The path of 3i Atlas takes it through our solar system at an angle, passing above the plane where most planets orbit, missing Earth by enormous distances, not just millions of miles, but distances measured in astronomical units, the same unit we use to describe the Earth-Sun separation. There was never any danger. There is no danger. This comet will never threaten Earth because its trajectory simply doesn't intersect with our orbit. It's passing through our solar system like a car on a highway that never exits, never enters the lanes where Earth is travelling, and in a few years it'll be too far away to observe, accelerating back into interstellar space on a journey that will take it who knows where. Maybe it'll encounter another stellar system in thousands or millions of years. Maybe it'll drift through the galaxy forever, a wanderer without a home, but it will never return here. This is a one-time event, a brief cosmic encounter, and then 3i Atlas is gone from our lives forever. So if 3i Atlas isn't a threat, what about UN271? This is where things get more interesting because UN271 isn't on a hyperbolic trajectory. It's on an elliptical orbit, a path that's bound to the Sun, a loop that will bring it inward from the Oort Cloud, around the Sun, and then back out to the Oort Cloud again. this comet is part of our solar system family. It belongs here, and eventually after completing its inward journey it will return. Not in our lifetimes, not in 1,000 lifetimes, but millions of years from now, UN271 will make another pass through the inner solar system. Right now, UN271 is inbound, falling toward the Sun on an orbit that astronomers have calculated with remarkable precision. They know where it's going. They know when it will reach its closest approach to the Sun. And here's that moment. In the year 2031, UN271 will reach perihelion, its closest point to the Sun. And even at that closest approach, even when it's as near to the Sun as its orbit will bring it, UN271 will still be approximately 11 astronomical units away. That's just beyond the orbit of Saturn. That's in the outer solar system, far beyond Mars, far beyond the asteroid belt, nowhere even close to Earth's orbit. Let me make this absolutely clear. UN271 will never come close to Earth. Its orbit doesn't bring it anywhere near the inner solar system where Earth resides. At its closest approach to the Sun, it will still be more than 10 times farther from the Sun than Earth is. There is no collision risk. There is no impact scenario. There is no threat in the conventional sense of a comet on a collision course with our planet. UN271 is enormous, yes. It's more massive than any comet ever observed, yes. But it's also following an orbit that keeps it safely distant, that never brings it into the region of space where Earth travels. So if neither object is going to hit Earth, if both trajectories keep them safely away from our planet, then what's the threat? Why did I title this video with the word Terrify? Why have we spent all this time comparing these objects if neither one is actually dangerous? And here's where we need to reframe what danger means, what threat really looks like when we're talking about cosmic objects and the long-term survival of our species and civilization. The threat isn't immediate. It's not about these two specific objects. 3i Atlas will never return. UN271 will never hit us. But what these objects represent, what they teach us, what they reveal about the universe we live in, that's where the real concern lies. That's where the word terrify shifts from meaning immediate physical danger to meaning something deeper, something about our place in the universe and our vulnerability to events we barely understand. UN271 is the answer to the question this video posed. UN271 is the object that should capture your attention, not because it's going to hit Earth, but because it represents a category of threat we haven't fully grasped. This comet is proof that the Oort Cloud contains objects far larger than we suspected. If one comet this massive exists, if it can form and survive in the frozen reaches of our solar system's edge, then there are probably others. We just haven't found them yet. They're out there, orbiting in the darkness, too distant to detect, waiting for some gravitational disturbance to nudge them onto orbits that bring them inward. And here's the uncomfortable truth. We don't know how many UN271 scale objects exist in the Oort Cloud. We don't have a census of the outer solar system. We've barely begun to map the population of large comets that could, under the wrong circumstances, be perturbed onto trajectories that bring them into the inner solar system. Most of the time, these objects stay safely distant, orbiting far beyond Neptune, never threatening the planets, but gravitational interactions are chaotic. Passing stars can disturb Oort Cloud orbits. Galactic tides can nudge comets toward the inner solar system. Over millions of years, over the entire history of Earth, countless comets have been scattered inward, and some of them have hit our planet. We know this because we have the geological evidence. We have impact craters. We have extinction events in the fossil record. We have evidence that large objects have struck Earth in the past, causing global devastation, wiping out species, fundamentally altering the course of life on our planet. The dinosaurs were killed by an impact, most likely from an asteroid. But comets have hit Earth too, and if a UN271 scale object was somehow perturbed onto a collision course with Earth, not this specific comet, but another one like it, something we haven't detected yet, the consequences would be catastrophic beyond any disaster in human history. That's the real terror. Not the immediate threat, but the long-term vulnerability. Not these two objects specifically, but what they represent about the population of things moving through space, the distribution of objects we haven't catalogued, the potential for something massive and undetected to be on a trajectory we don't know about. UN271 is a wake-up call. It's a reminder that our solar system contains giants, that the Oort Cloud is not just a reservoir of small harmless comets, that we need to be vigilant about watching the sky and detecting objects while they're still far away, while we still have time to understand their orbits and assess any potential threat. And this is where the comparison with 3i Atlas becomes meaningful. 3i Atlas is exciting because it's from another star, because it gives us insights into interstellar objects and planetary formation around other stars. But 3i Atlas is also a one-time visitor. It's here and then gone. It doesn't represent an ongoing threat. It doesn't tell us anything about our own vulnerability because it's not part of our solar system's population. It's just passing through. UN271, on the other hand, is part of our family. It's one member of a vast population of comets that orbit in the Oort Cloud, any one of which could, under the right circumstances, be nudged inward. And the fact that it's so large, the fact that it defies what we thought we knew about maximum comet sizes, suggests that our understanding of the Oort Cloud population is incomplete. We've been underestimating what's out there. We've been assuming that all long-period comets are relatively small, that nothing on the scale of UN271 exists, that the giants are all in the asteroid belt or in stable orbits that don't threaten Earth. UN271 proves we were wrong. So when I ask which one should terrify you, when I compare the interstellar stranger to the giant from our own backyard, the answer is clear. UN271 matters more, not because it's going to hit us, not because it poses an immediate danger, but because it represents a gap in our knowledge, a vulnerability we haven't fully addressed, a category of objects that could, over the long timescales of planetary history, pose genuine risks to Earth. The terror isn't panic. It's not the fear of imminent destruction. It's the realization that we live in a universe where massive objects orbit in the darkness, where gravitational interactions are unpredictable over millions of years, where we need to keep watching and learning and improving our detection capabilities if we want to protect our planet over the centuries and millennia ahead. And that realization brings us to the next crucial question. What are we learning from these objects? What scientific value do they provide? What can they teach us that justifies the attention and resources and telescope time we're dedicating to observing them? Because understanding threat is important, but so is understanding opportunity, the chance to learn something new, to advance our knowledge, to gather data that helps us understand not just these two objects, but the entire universe they represent. Science isn't just about identifying threats. It's not only about calculating orbits and assessing danger and making sure we're safe from cosmic collisions. Science is also about curiosity, about understanding, about taking advantage of rare opportunities to learn something new about the universe we inhabit. And both 3i Atlas and UN271 are providing exactly that kind of opportunity. Chances to study objects we don't normally get to observe, to gather data that tells us about planetary formation and comet composition, and the processes that shape solar systems both here and in the distant reaches of the galaxy. Let's start with what 3i Atlas is teaching us, because every interstellar object that passes through our solar system is a gift to science. We can't travel to other star systems. We can't send probes to study planets around other stars, at least not with current technology and not within any reasonable time frame. The distances are too vast, the journey times too long. But when an interstellar object comes to us, when it falls through our solar system on a trajectory we can observe, it brings us samples of another stellar system's composition. It brings us data we could never gather any other way. 3i Atlas is giving us insights into what comets from other star systems are made of. Every spectrum we capture, every measurement of the gases being released as it approaches the Sun, every image of its coma structure and tail morphology, all of this data tells us about the building blocks of another planetary system. We've been measuring water vapor, carbon dioxide, carbon monoxide, dust composition, organic molecules. We've been comparing these measurements to what we see in our own solar system's comets, looking for similarities and differences, trying to understand what's universal about comet formation and what's specific to particular stellar environments. And what we're finding is fascinating. 3i Atlas looks remarkably similar to solar system comets. Its composition isn't radically different. Its behavior as it heats up and outgasses isn't exotic or mysterious. This suggests that planetary formation, at least in the region where comets form, follows similar processes across different stellar systems. The chemistry is similar. The mix of ices and rocks and organic compounds is comparable. This is actually profound, because it tells us that the conditions that create comets, cold temperatures, abundant ices, gradual accretion of material, produce similar results whether we're talking about our Sun or some distant star dozens of light years away. The non-gravitational forces we're observing in 3i Atlas are also teaching us about comet structure and activity. When a comet outgasses, when jets of material erupt from its surface, those jets create forces that can change the comet's rotation or slightly alter its trajectory. These are tiny effects, but they're measurable, and they tell us about where active regions are located on the nucleus, how material is distributed beneath the surface, how the comet is responding to solar heating. For 3i Atlas, we're seeing complex tail structures, multiple jets, evidence of active regions that are producing outflows of gas and dust. This is valuable data about how interstellar objects behave when they encounter a star after travelling through the cold of interstellar space. And then there's the comparison with previous interstellar visitors. We can now compare 3i Atlas to 2i Borisov, the previous interstellar comet, and see what's similar and what's different. 2i Borisov also looked remarkably comet-like, also had composition similar to solar system comets. The pattern is becoming clear. Interstellar comets aren't exotic oddities. They're similar to what we see in our own solar system, which suggests that the processes of planetary formation are relatively consistent across the galaxy. This has implications for astrobiology, for understanding how many planetary systems might have the right conditions for life, for estimating how common Earth-like worlds might be among the hundreds of billions of stars in our galaxy. UN271 is teaching us different lessons, but equally important ones. This comet is giving us access to pristine material from the early solar system, composition data that hasn't been altered by repeated passes through the inner solar system. The carbon monoxide jets we're observing, even though UN271 is still far beyond Neptune, are particularly revealing. Carbon monoxide is more volatile than water ice. It sublimates at lower temperatures. The fact that UN271 is actively outgassing carbon monoxide at such extreme distances tells us about the internal structure of this giant comet, about how heat penetrates into its interior, about what kinds of ices are present beneath the surface. The ALMA observations have been crucial here. ALMA is one of the most powerful radio telescope arrays on Earth, capable of detecting the faint signatures of molecules in space. When ALMA looked at UN271, it detected carbon monoxide streaming from the comet's nucleus, and by measuring the amount and distribution of this gas, scientists could estimate how much material UN271 is shedding, how active it is, what this tells us about its composition. This is data we simply couldn't get from telescopes that only observe visible light. ALMA sees the molecular emissions, the chemical signatures, the specific compounds being released. Hubble Space Telescope observations have been equally important. Hubble has the resolution to separate the tiny nucleus of UN271 from the surrounding coma, to measure the size of the solid core, to confirm that this comet really is as massive as initial estimates suggested. Without Hubble, we'd have only rough size estimates based on brightness and assumptions about albedo. With Hubble, we have precise measurements, confirmed data that establishes UN271 as the largest comet nucleus ever observed. What UN271 is teaching us about the Oort Cloud is perhaps its most important scientific contribution. Before this discovery, we thought we understood the size distribution of comets in the Oort Cloud. We thought they were all relatively small, that the largest long-period comets had nuclei maybe 20 or 30 miles across at most. UN271 shattered that assumption. It proved that the Oort Cloud can produce, and has produced, objects far larger than we suspected. And if one giant exists, then the population models need to be revised. There are probably other UN271 scale objects out there, orbiting in the darkness, waiting to be discovered. This has implications for planetary formation theory. How do you grow a comet this large? What conditions in the early solar system allowed UN271 to accrete this much material before being scattered into the Oort Cloud? The answers to these questions tell us about the density and distribution of material in the protoplanetary disk, about the timeline of planetary migration, about the chaos of the solar system's early history, when giant planets were still settling into their orbits and scattering smaller bodies in all directions. We're also learning about how giant comets behave over long timescales. Most of the comets we observe are much smaller than UN271, and they make frequent passes through the inner solar system, losing volatiles each time, gradually becoming less active until they're essentially dead nuclei with no gas or dust production. UN271, because of its enormous size and its long-period orbit, is different. It has so much mass, so many volatiles, that even after multiple passes through the inner solar system over billions of years, it's still active. It still has enough subsurface ice to produce outgassing. This tells us something about the lifetime of comets, about how long they remain active, about what fraction of Oort Cloud objects might still have the potential to produce spectacular displays if their orbits bring them close enough to the Sun. And then there's the planetary defense aspect, which we'll explore more deeply in the next section. But for now, what matters is that both 3I Atlas and UN271 are teaching us about detection, about observation, about how we find and track objects in the solar system. 3I Atlas was detected relatively late, when it was already approaching the inner solar system, because interstellar objects are faint and move on unexpected trajectories that don't match the search patterns designed to find solar system objects. UN271 was detected years before its closest approach, because it's large enough to reflect significant sunlight even at extreme distances. These detection timelines matter. They tell us about the limits of our current survey programs, about what we can see and what we're missing, about where we need to improve if we want comprehensive awareness of everything moving through our cosmic neighbourhood. The observation campaigns themselves are remarkable achievements. Astronomers around the world are coordinating their efforts, sharing telescope time, combining data from multiple instruments to build the most complete picture possible of both objects. Amateur astronomers are contributing too, capturing images, making measurements, adding to the dataset that professional scientists analyse. This is modern astronomy at its best, collaborative, comprehensive, taking advantage of every available resource to squeeze as much knowledge as possible from rare cosmic opportunities. But while we're learning from what we can observe, what about what we can't see? What about the objects that are too distant, too faint, or on trajectories we haven't detected yet? What about the population of comets and asteroids that could, under different circumstances, pose genuine threats to Earth? That's where the science of observation meets the urgency of planetary defense, and that's what we need to explore next. The real hidden danger that UN271 represents, not the comet itself, but what it tells us about everything else lurking in the darkness. We've established that neither 3I Atlas nor UN271 poses a direct threat to Earth. Their trajectories keep them safely distant. Their orbits don't intersect with our planet's path. But here's where the conversation shifts from these two specific objects to the broader implications of what they represent. Because the real threat isn't the comets we can see and track and predict. The real threat is the population of objects we haven't detected yet, the giants hiding in the darkness of the Oort Cloud, and the asteroids we haven't catalogued, and the interstellar visitors that might arrive on trajectories we're not watching for. The Oort Cloud is estimated to contain trillions of comets. Trillions. That's not an exaggeration. That's the scientific consensus based on models of solar system formation and the scattering processes that flung countless icy bodies into the outer reaches of the Sun's gravitational influence billions of years ago. Most of these comets are small, the typical few-mile-wide nuclei that occasionally get perturbed onto orbits, bringing them into the inner solar system. But UN271 proved that some of them are enormous, far larger than we suspected, massive enough to cause extinction-level devastation if they were somehow redirected onto collision courses with Earth. And here's the problem. We don't have a complete inventory of the Oort Cloud. We can't see most of it. Objects in the Oort Cloud orbit at such extreme distances, thousands of times farther from the Sun than Earth, that they reflect almost no sunlight. They're invisible to our telescopes unless they happen to pass in front of a background star, or unless they start approaching the Sun and begin outgassing. Most Oort Cloud comets remain undetected until they're already inbound, already falling toward the inner solar system, already on trajectories we need to understand and predict. This creates a timing problem. For asteroid defense, for protecting Earth from impacts, time is everything. If we detect a threatening object decades in advance, we have options. We can study its orbit precisely. We can plan missions to deflect it, to change its trajectory slightly, so that instead of hitting Earth, it misses us entirely. We've proven we can do this. NASA's DART mission successfully altered the orbit of an asteroid by intentionally crashing a spacecraft into it. The technology works. The physics is understood, but it requires advance warning. It requires knowing that a threat exists while it's still far away, while we still have years or decades to plan and execute a deflection mission. Long-period comets from the Oort Cloud are harder to track than near-Earth asteroids. Asteroids orbit in the inner solar system, mostly in the belt between Mars and Jupiter. They're relatively close, relatively bright, and they orbit in predictable patterns that our survey programs are designed to detect. We've catalogued most of the large near-Earth asteroids, the ones big enough to cause global devastation. We know where they are, where they're going, whether any of them pose risks in the coming centuries. The asteroid threat is largely understood and manageable. But comets are different. Long-period comets can come from any direction. They don't orbit in the plane where most planets travel. They can approach from above or below from angles our survey programs aren't optimized to detect. And because they spend most of their time in the distant Oort Cloud, we don't know they exist until they're already inbound, until they've been perturbed onto trajectories bringing them toward the Sun. By the time we detect a long-period comet, it might be only months or a few years from its closest approach to the Sun. That's not enough time to plan and execute a deflection mission if the comet turns out to be on a collision course with Earth. UN271 is a case study in what happens when we get lucky with detection. This comet was spotted years before its closest approach, captured in survey images when it was still far beyond Neptune. That early detection gives us years to study it, to understand its orbit, to track its approach. If UN271 were on a collision course with Earth, which it absolutely is not, but hypothetically, we would have had enough warning time to do something about it. We would have had the decades needed to plan and execute a deflection mission, but UN271 was only detected because it's enormous. Smaller comets, even ones large enough to cause devastating impacts, might not be visible until they're much closer, until they start out gassing and producing coma that makes them bright enough to detect. And that raises the uncomfortable question: how many UN271 scale objects are in the Oort Cloud that we haven't detected yet? How many objects large enough to threaten Earth are orbiting in the darkness, waiting for some gravitational perturbation to send them inward? We don't know. We can't know with current technology. Our survey programs are improving. New telescopes are coming online. New detection algorithms are being developed. New sky surveys are cataloguing fainter and fainter objects. But the Oort Cloud is vast, and the population of objects out there is largely invisible to us. We're essentially blind to most of what exists in the outer reaches of our own solar system. And then there's the interstellar dimension. 3i Atlas reminds us that objects from other stellar systems can pass through ours. We've now confirmed 3 interstellar objects: Oumuamua, 2i Borisov, and 3i Atlas. That's 3 in just a few years of heightened awareness and improved detection capabilities. How many interstellar objects pass through our solar system without being detected? How often does the solar system encounter wanderers from other stars, objects that we never see because they're too faint, or because they don't pass close enough to the Sun to start outgassing? Most interstellar visitors probably aren't threats. They're passing through on hyperbolic trajectories, here and gone, never coming close to Earth. But statistically, over millions of years, over the entire lifetime of Earth, some interstellar object has probably had a close encounter with our planet. Maybe one has even hit us. We wouldn't necessarily know from the geological record. A comet impact from billions of years ago would look the same whether the comet came from our solar system or from interstellar space. The detection challenge is real and ongoing. We need better telescopes, more comprehensive survey programs, more sophisticated algorithms that can identify faint moving objects against the background of stars. We need to expand our search to include trajectories that don't match typical solar system orbits, paths that might indicate interstellar visitors. We need to watch the sky continuously, cataloguing everything, tracking everything, building a comprehensive map of what's moving through our cosmic neighbourhood. And this is where funding matters, where political will matters, where public awareness matters. Planetary defence isn't sexy. It doesn't produce immediate results. It's the kind of long-term preventative work that's easy to defund when budgets get tight, easy to dismiss as low priority compared to more pressing concerns. But the consequences of not doing this work, of not maintaining and expanding our detection capabilities, could be catastrophic. All it takes is one object we didn't see, one trajectory we didn't predict, one impact we could have prevented if we'd only been watching more carefully. UN271 is a reminder of this vulnerability. It's proof that our solar system contains objects we didn't know about, giants hiding in plain sight, threats we would have missed entirely if we hadn't been running comprehensive sky surveys that happened to capture this comet in their images. And if one UN271 exists, if the Oort Cloud can produce something this massive, then our models of the comet population are incomplete. We've been underestimating what's out there. We've been assuming that the largest long-period comets are smaller than they actually can be. This isn't cause for panic. It's not reason to live in fear of the sky. Earth has been here for billions of years, surviving countless impacts, continuing to support life even after events that caused mass extinctions. The probability of a large impact in any given century is low. But it's not zero. And over long enough timescales, over thousands or millions of years, large impacts are not just possible but statistically certain. The question isn't whether another major impact will happen. The question is when, and whether we'll see it coming in time to do something about it. This is why UN271 matters more than 3i Atlas in the context of threat assessment. 3i Atlas is a visitor, a one-time event, something that teaches us about interstellar space but doesn't tell us much about our own vulnerability. UN271 is part of our solar system family. It's one member of a vast population of objects that could, under the right circumstances, pose genuine risks to Earth. It's a wake-up call, a reminder that we need to keep watching, keep improving our detection capabilities, keep funding the survey programs and planetary defense initiatives that might one day save civilization from a preventable catastrophe. And that brings us to the final part of our comparison. The conclusion that ties everything together, your role in this story, what these discoveries mean for human civilization, how we should think about cosmic threats, and why staying informed about these objects matters even if they're never going to hit us in our lifetimes. So here we are at the end of this journey, having compared two cosmic giants from radically different origins, having traced their paths and assessed their threats, and understood what they teach us about the universe. And now I want to bring this back to you, to the person watching this video, to the human being who chose to spend these minutes learning about comets and trajectories and the hidden dangers lurking in the darkness of space. Because this isn't just an academic exercise. This isn't just about satisfying curiosity or understanding astronomy. This is about your place in a larger story, about living in an era when humanity finally has the capability to see threats coming and potentially do something about them. Think about what that means for all of human history, for the entire existence of our species. We've been vulnerable to cosmic impacts without any warning, without any ability to predict or prevent them. The dinosaurs didn't see the asteroid coming. The countless species that went extinct in previous impact events had no awareness that something was falling from the sky until it was too late. Every civilization that ever looked up at the stars did so without understanding that some of those moving lights might one day fall toward Earth with catastrophic consequences. But you live in the first generation of humans who can detect these objects while they're still far away, who can calculate their orbits, who can predict their paths and assess their threat levels. You live in an era when we have telescopes powerful enough to spot comets in the outer solar system, when we have spacecraft capable of reaching asteroids and altering their trajectories, when we have the mathematical tools and computational power to model orbital mechanics and understand where everything is going. This is unprecedented in the history of life on Earth. This is a capability that's only emerged in the last few decades, and it's still improving, still expanding, still becoming more comprehensive with each new survey program and each new telescope that comes online. 3i Atlas and UN271 are symbols of this new awareness. They're examples of what we can detect, what we can track, what we can learn from when we dedicate resources and attention to watching the sky. 3i Atlas showed us that interstellar objects pass through our solar system more often than we thought, that we're surrounded by a galaxy full of wandering comets and asteroids ejected from other stellar systems. UN271 showed us that our own solar system contains giants we never suspected, that the Oort Cloud is more complex and more populated with massive objects than our models predicted. And here's what matters. These discoveries only happened because people, scientists, engineers, telescope operators, data analysts, chose to do the work. They chose to build survey programs. They chose to sift through millions of images looking for moving objects. They chose to follow up on faint detections that most people would have dismissed. They chose to dedicate their careers to understanding what's out there, to mapping the population of objects moving through space, to building the knowledge base that might one day protect civilization from a catastrophic impact. Your role in this story is to be informed, to be aware, to understand that this work is happening and why it matters. Because public awareness drives funding. Funding drives technology development. Technology development drives better detection capabilities. Better detection capabilities drive earlier warnings, and earlier warnings give us options, give us time, give us the ability to protect ourselves from threats that previous generations could only pray wouldn't happen in their lifetimes. You don't have to be an astronomer to contribute to this. You don't need a telescope or a degree in orbital mechanics. What you need is to care, to pay attention, to support the institutions and programs that do this work. Space agencies like NASA and ESA and others around the world, they're the ones building the telescopes, launching the survey missions, developing the deflection technologies that could one day save billions of lives. But they operate on budgets that are determined by political processes, by public priorities, by how much society values this kind of long-term, preventative work. When you share information about objects like 3I Atlas and UN271, when you talk about these discoveries with friends or family, when you engage with space science content, you're helping to build the public awareness that supports continued funding for planetary defense. You're part of the chain that connects scientific discovery to political will, to resource allocation to the actual programs that keep us safe. This isn't abstract. This isn't disconnected from your life. This is how societies make collective decisions about priorities and risks and where to invest limited resources, and there's more coming. UN271 is approaching its closest point to the Sun in the year 2031. We have years of observation ahead, years to study this giant as it gets closer, as solar heating increases its activity, as we learn more about its composition and structure and behaviour. Every data point we gather from UN271 adds to our understanding of giant comets, of Oort Cloud populations, of what might be lurking in the frozen reaches of our solar system. 3I Atlas, meanwhile, is fading from view. It's moving away from the Sun, getting fainter, becoming harder to observe. In a few years, it will be beyond the capabilities of even our most powerful telescopes to detect. But the data we've gathered will remain, will be analysed for years to come, will contribute to our understanding of interstellar objects and what they tell us about planetary systems throughout the galaxy. There will be more discoveries. There will be more interstellar visitors detected as our survey programs improve. There will be more giant comets found in the Oort Cloud as we push our detection capabilities to greater distances and fainter objects. Each discovery will add to the picture, will help us understand the population of objects moving through space, will improve our ability to predict and respond to potential threats, and maybe, someday, we'll detect an object that is on a collision course with Earth. Maybe it'll be decades away, maybe a century, maybe it won't happen for thousands of years. But when it does happen, not if, but when. The response will depend entirely on the infrastructure we've built, the knowledge we've accumulated, the technologies we've developed, the warning time we've gained through comprehensive detection programs. Everything we're learning from objects like 3I Atlas and UN271, every improvement we make to our survey capabilities, every mission we launch to study asteroids and comets, all of it builds toward the moment when we might need to act, when we might need to deflect a threatening object, when the difference between survival and catastrophe depends on whether we saw the threat coming in time. So when I ask which one should terrify you, when I compare the interstellar stranger to the giant from our own backyard, the answer is that neither should inspire panic, but both should inspire action. Not fear, but awareness. Not anxiety, but motivation to support the work that keeps us safe. UN271 matters more in terms of long-term threat assessment, because it represents a population of objects we're only beginning to understand, because it proves that our solar system contains giants we haven't fully catalogued, because it reminds us that vigilance is necessary and detection capabilities need to keep improving. But 3I Atlas matters too, because it shows us that the universe is full of wandering objects, that we're not isolated, that we're surrounded by a galaxy where ejection and scattering are common processes. Both objects teach us something valuable, both contribute to our understanding, both remind us that space is not empty, that our planet moves through a cosmic environment full of potential threats, and that awareness is our best defense. You've stayed with me through this entire exploration. You've learned about two cosmic giants, compared their sizes and origins and trajectories, understood what they mean for science and for planetary defense. Now take that knowledge and do something with it. Subscribe to this channel if you want to stay informed about the next cosmic discovery, the next object that teaches us something new, the next advance in our ability to see and understand and protect ourselves from what's out there. Share this video with someone who needs to understand that the universe isn't empty, that threats exist but knowledge reduces fear, that we live in an era when awareness and action can make the difference between catastrophe and survival. And tell me in the comments, after everything we've covered, which one do you think deserves more attention? The interstellar stranger passing through on its way to somewhere else? Or the giant from our own solar system's frozen edge that represents a population we're only beginning to understand? I genuinely want to know where you stand, what you think matters more, what captured your attention in this comparison. Because these conversations matter, they build awareness. They create the public engagement that supports the work that might one day save civilization. The universe isn't trying to scare us. It's not hostile. It's not malevolent. It's indifferent. It's full of objects moving on trajectories determined by gravity and momentum and the chaotic interactions of billions of years of planetary dynamics. Some of those trajectories eventually intersect with Earth. That's not a threat designed to harm us. It's just physics, just mathematics, just the way orbital mechanics works over long enough timescales. But we have the capability now to see those trajectories, to predict them, to change them if necessary. We have the tools to protect ourselves if we choose to use them, if we maintain the vigilance and the commitment to watch the sky and understand what's moving through it. Until the next cosmic mystery reveals itself, until the next discovery changes what we thought we knew, until the next object falls into our solar system and gives us new opportunities to learn, stay curious, stay informed, stay engaged with the science that's mapping our cosmic neighbourhood. Keep looking up, but not with fear. Look up with wonder, with appreciation for living in an era when we can finally see what's coming, with gratitude for the scientists and engineers who dedicate their lives to keeping watch over the darkness. Look up knowing that knowledge is power, that awareness is protection, that every discovery brings us closer to true cosmic citizenship, not just inhabitants of Earth, but conscious participants in a universe full of wonders and challenges and opportunities to grow beyond what we thought possible. The giants are moving through space, some from distant stars, some from our own frozen reaches, and we, fragile, curious, determined, we're watching them, learning from them, building the knowledge that might one day ensure our survival across the vast expanses of cosmic time. That's not terrifying, that's extraordinary, and you're part of it, simply by being here, by learning, by caring enough to understand what's really out there in the darkness between the stars.